We have been discussing about the electrostatic potential and electrostatic field and have dealt with many different situations. I want to get a little more sophisticated now in using the Poisson's and Laplace's equation and develop a little more sophisticated techniques and learn to deal with these equations. Of course, when I come back later to electrostatics again after a few more lectures which I will do, which I will use for doing magnetic fields and electrodynamics, then we will be more sophisticated and even more sophisticated in dealing with these equations. So, right now I want to focus on Poisson's equation and Laplace's equation, along with them the boundary conditions, and see what all can we extract out of this. In this lecture, I am going to do something called the Green's identity that can be used to develop Green's function method. To solve Poisson's equation, but I am not going to deal with that today. What I will instead focus on is something called the reciprocity theorem. And its interpretation. So, this part I am not dealing with. We will come back to it later in the course. Today I will focus on reciprocity theorem. For that, I will develop Green's identities first. So, recall that you have del square V equals minus rho over epsilon 0. Let us take two potentials V 1 and V 2 corresponding to two different charge densities and boundary conditions in, and this is very important, the geometry remains the same in a given volume with a surface, and this remains unchanged in both the cases. So, let us see what the equation is. If I take divergence of V 1 grad of V 2, this will be equal to grad of V 1 dot grad of V 2 plus V 1 grad square V 2. Now, given this volume that I said is fixed, right, this is the volume, talking about this volume inside this shaded region. So, this is the volume. Let us now integrate this over this volume. So, I have integration of divergence of V 1 grad of V 2 dV is equal to integration grad V 1 dot, let us erase this, grad V 2 dV plus integration V 1 grad square V 2 dV. So, the left hand side by divergence theorem is going to be integral V 1 grad of V 2 dot ds. Now, in this volume, ds is going to be pointing out. So, let us make that ds is going to be pointing out everywhere. This is the normal n, right. Let us make it everywhere. So, I can write this integral as equal to V 1 grad of V 2 dot n integration ds, which symbolically most of the books are going to write as V 1 grad V 2 or partial V 2 with respect to n ds. That is the left hand side. Let us go to the next slide. And therefore, I get in this volume V 1 grad V 2 partial V 2 and ds is equal to integration grad V 1 dot grad V 2 ds dV plus integration V 1 Laplacian of V 2 dV. This is known as Green's first identity. This is Green's first identity. From this, I am led to Green's second identity, which leads to reciprocity theorem. So, what I am going to do is switch V 1 and V 2 in the first identity. And that gives me integration V 2 dV 1 dN ds is equal to integration grad V 2 dot grad V 1 dV plus integration V 2 del square V 1 dV. Now, we will subtract second equation from the first one to get integration V 1 partial V 2 partial n minus V 2 partial V 1 partial n integrated over the surface of this volume is equal to, the first term cancels, the 2 gradient product cancels, and I get V 1 del square V 2 minus V 2 del square V 1 dV, and this is known as Green's second identity. This is useful. So, let me remark here, Green's second identity leads to Green's function method. Solving the Poisson's equation. But we are not doing that right now. I want to use it for something else. So, let us go to the next slide. Integration V 1 dV 2 by dN minus V 2 dV 1 by dN ds is equal to V 1 grad square V 2 minus V 2 grad square V 1 integration dV for a given volume. And let me again remind you that this n means I am taking this derivative going out. Let us interpret this physically. So, let us interpret this identity physically in terms of charges. So, let us say in this volume I create 2 situations, whereby in one situation I had charge density rho 1, sigma 1 on the surface, and in the other situation I have charge density rho 2 and sigma 2 on the surface. And let us say these boundaries, so let me make it slightly thicker, are conducting. So, I have this cavity in a conducting shell. I know that del square V 1 is equal to minus rho 1 over epsilon 0, del square V 2 is equal to minus rho 2 over epsilon 0. What about the other term d V 1 by d n? This is nothing but n dot grad of V 1, which is minus n dot E 1, right. So, and we are talking about the surface, this is we are talking about at the surface. So, let me make this a little pillbox here. With one side inside and the other side in the conductor, and apply Gauss's law. So, here I have this box, this is grad of V with a minus sign. Here E is 0. So, if I do the Gauss's law, I am going to get minus n, because the normal out here is going to be minus n dot minus grad v is equal to sigma over epsilon 0, or dv dn is equal to sigma over epsilon 0. This is a slight calculation to relate dv dn to sigma over epsilon 0, or the surface charge. So, I can write this dv 1 by dn is equal to, I can come back here and write this equal to sigma 1 over epsilon 0. Similarly, for the right hand side, I am going to have dv 2 by dn is equal to n grad of v 2, which is minus n dot E 1, which is going to be sigma 2 over epsilon 0. And now, I will collect all the terms and see if I put them in Green's second identity, what do I get. So, let us do that in the next slide. I have v 1 grad v 2 over n partial v 2 over partial n minus v 2 partial v 1 over partial n ds integration is equal to integration v 1 del square v 2 minus v 2 del square v 1 dv. And we have just written that dv 2 by dn is equal to sigma 2, dv 1 by dn is equal to sigma 1 over epsilon 0 over epsilon 0, del square v 2 is equal to minus rho 2 over epsilon 0, del square v 1 is equal to minus rho 1 over epsilon 0. If I put it all together in the equation for Green's second identity, I get v 1 sigma 2 over epsilon 0 ds minus v 2 sigma 1 over epsilon 0 ds is equal to integration minus v 1 rho 2 over epsilon 0 dv plus integration v 2 rho 1 over epsilon 0 dv. Collecting terms with the charge density in the second case and the charge density in the first case together, I get integration v 1 sigma 2 ds plus integration v 1 rho 2 dv is equal to integration v 2 sigma 1 ds plus integration v 2 rho 1 dv. I am going to call this the reciprocity theorem. What does it do? The theorem relates potential of one particular charge density times the charge density for another situation. Two, what is it related to? These quantities. Interchange. So, I took V1 for charge density rho 1 and multiplied by the other charge density sigma 2 and rho 2 and related it to these quantities interchange. This is known as the reciprocity theorem, and it can be used in certain situations to find charge densities in a particular situation using some other situation for the same geometry. Let us first do an example of that, and then I will interpret it. I will derive this and interpret this in terms of the energy calculation. So, let us do an example. Example is, recall when we had a grounded sphere and we had a charge q in front. There was some charge induced here, q prime, and that actually represented the sigma theta, such that sigma theta d s was equal to q prime. So, the question I am asking is, calculate the total charge induced on a grounded sphere due to a point charge q in front of it. By applying reciprocity theorem. So, to apply reciprocity theorem, I got to create two different situations. So, to apply reciprocity theorem, two different situations need to be considered. And one of these is the problem to be solved. So, let us say the problem I am solving is this grounded sphere and q in front of it at a distance d z from the center, and let us take this to the center to be the origin. Then I have rho 1 is equal to q delta of r minus d z integration sigma 1 d s. I want to find out V 1 on the surface is equal to 0. That is situation 1. Situation 2 is I will take this sphere to be carrying some charge q and isolate it from the ground. So, this is through some insulator, it is kept somewhere. Again, center is the origin. This has charge q. This is metallic sphere, so charge q is going to be spread over the surface. I have rho 2 to be equal to 0, sigma 2 is equal to q over 4 pi r square, where r is the radius. V 2 surface is equal to q over 4 pi epsilon 0 r, and V 2 at r is equal to q over 4 pi epsilon 0 r. On the surface, obviously, the radius of the sphere comes in. So, we have created two situations. The first one is original, and we want to apply this, the reciprocity theorem, to this. So, let us do that. I have integration V 1 sigma 2 ds plus integration V 1 rho 2 ds is equal to integration V 2 sigma 1 ds, this is not ds, this is dv, plus integration V 2 rho 1 dv. The potential on the surface in the first situation is 0 because it is a grounded sphere, and rho 2 is 0. So, the integration on the left is 0. What this leads to then is that 0 equals V 2 on the surface is q over 4 pi epsilon 0 r. I want to find sigma 1 ds, that is the induced charge, plus rho 1 has a delta function. So, this will give me the value of V 2 at that distance. So, I get q over 4 pi epsilon 0 d. This immediately leads to integration sigma 1 ds is equal to, or there is a q also here, sigma 1 ds equals minus q r over d, which indeed was the induced charge, is the total. So, you see, through a situation, through creating two situations, I could find what the induced charge is. Similar problem I will leave for you to do is, given a metallic conductor, no charge, isolate it from the ground, net charge on this is 0, and I keep a charge q in front at a distance d, radius is r. Find the electrostatic potential on the sphere using reciprocity theorem. Again, create two situations. This time what you want to find is V on the surface of the sphere, which will be the same as throughout the sphere. Now, let us interpret or rather derive reciprocity theorem from energy considerations. So, you see, I derived it using mathematical identities, interpreted this in terms of charges. Now, we will do energy considerations. So, given a volume inside a conductor. So, this is a thick conductor. Now that I know there is a thick one, so I can do that. There is a charge density rho 1 inside, and there is some sigma 1, and the potential all over is V 1. Then I know that the energy of the system is W 1, which is equal to 1/2 integration rho 1 V 1 dV plus 1/2 sigma 1 V 1 ds. I change this rho 1 to rho 2. So, change rho 1 to rho 2, so that V 1 goes to V 2 and sigma 1 goes to sigma 2. If I do that, then the new energy W2 is going to be equal to integration 1/2 rho 2 V2 dV plus 1/2 integration sigma 2 V2 ds. So, I can calculate W2 minus W1 by subtracting W1 from W2 directly in the formula. Another way to calculate this change will be, I am changing from rho 1 to rho 2, then somewhere along the way I can take a rho as a function of fractional change, which will be equal to rho 1 plus f times rho 2 minus rho 1. F varies from 0 to 1. Recall the derivation earlier when we were calculating the energy for a charge distribution. And consequently, the potential will also be along the way equals V 1 plus f V 2 minus V 1, f again being between 0 and 1. So, I can calculate the change in the energy somewhere along the way when I have potential to be V f, I change the charge density by d f rho 2 minus rho 1, then total energy change delta W, which is W 2 minus W 1 will be equal to integration 0 to 1 d f V f rho 2 minus rho 1. Whatever that comes out to be, which will be equal to 0 to 1 d f V f is V 1 plus f V 2 minus V 1 times rho 2 minus rho 1. This will also give delta W. Next, what we do is equate delta W equals 1/2 rho 2 V 2 dV plus 1/2 rho 1 rho 2 V 2 ds. Sorry, I will erase this. Plus 1/2 sigma 2 V 2 ds minus 1/2 rho 1 V, what did I, rho 1 V 1 dV minus 1/2 sigma 1 V 1 ds is equal to this integral that I just calculated 0 to 1 df, the integral that I just wrote V 1 plus f V 2 minus V 1 rho 2 minus rho 1. This will lead to reciprocity theorem, and this is left as an exercise for you. You will also find during the exercise that I have left one term here. There should be one more term related to sigma term. There will be a sigma term also. That will give you the reciprocity theorem. Let us use this theorem once more to solve another problem part of which we did earlier. So, problem example 2, recall the problem of charge in front of a grounded plane, grounded conducting plane. The problem was that we had a plane which was grounded and there was a charge q in front of it. What we want to do now is make this problem more complicated and ask, if I have two grounded planes, like in a parallel plate capacitor, they are not grounded, but I am grounding them now. So, plates are like in a grounded in a parallel plate capacitor, infinitely large. So, they are extending, and I put a charge q between them at a distance, let us say x from the left plate. The distance between the plates is d. If you solve this problem through image problem, you will run into trouble, because this q would have a minus q here and minus q here. Then these minus q will again give you an image, this will give you an image, and therefore, you will make an infinite number of images. Summing them would be very, very difficult. So, if I want to find the induced charges on the plates, I will apply reciprocity theorem. So, the problem is to find induced charge total on each plate. And here I will use reciprocity theorem. So, I will create two different situations. One of those situations will be my original problem. This plate, another plate, both are grounded. Let us take this direction to be x, and here is a charge right here q at a distance x from the left plate, and the distance between the two plates is d. So, in this case, V1 on the surface is 0. Let us take the left plate to be the at the position x equals 0. So, that I have rho 1 is equal to q delta of r minus x integration sigma 1 on the left plate ds I want to find out, and I also want to find out sigma 1 on the right plate ds is equal to 0. This is what I want to find out. This is situation 1. Let us create another situation. So, situation 2. What I will do is, I will take the left plate and not ground it, and the right plate I still will ground it, and put some charge density sigma per unit area on the left plate, which will induce a charge density minus sigma on the right plate. So, rho 2, there is no bulk charge, is 0. Sigma 2 on the left plate is some sigma. Sigma 2 on the right plate is equal to minus sigma. This will create an E field going to the right, which will be sigma over epsilon 0, and therefore, V on the left plate on the surface is going to be sigma d over epsilon 0. So, let us write V2 on the left plate is equal to sigma d over epsilon 0, and V2 as a function of x is going to be sigma over epsilon 0 d minus x. So, that when x equals d, V2 is 0, which is on the right plate, and x equals 0 is sigma d over epsilon 0. So, we have all the ingredients now. Let us apply reciprocity theorem. Which says integration V1 rho 2 dV plus V1 sigma 2 dV is equal to V2 rho 1 dV plus V2 sigma 2 should be sigma 1, that is what I am going to find out, sigma 1 ds. Now, V1 on the surface, this should be ds. V1 on the surface is 0, and therefore, this term is 0. Rho 2 is 0, therefore, this term is 0. So, I get 0 equals rho 1 is q delta at x. So, I am going to get V2 value there, which is sigma over epsilon 0 d minus x times q, plus V2 on the right plate is 0, and V2 on the left plate is sigma over epsilon 0 d, and this is what I want to find out, sigma 1 ds on the left plate. This immediately gives me sigma 1 ds on the left plate is equal to minus q d minus x over d. So, we got the answer for the left plate. Next is, what about charge on the right plate? For that, I will have to create another situation, and what we will do in this case is, we will take these two plates, and this time I am going to ground the left plate and put a charge sigma here, so that on the surface is minus sigma here, V is 0, and this time V2 x is going to be sigma over epsilon 0 x, because the field is going to the left. Sigma 2 left is minus sigma, sigma 2 right is plus sigma, and rho 2 is 0. Again, apply reciprocity theorem, and you are going to get integration sigma ds on the right plate is equal to sigma 1 ds on the right plate to be equal to minus q x over d. This is left as an exercise. So, what we did in this lecture is played around with the Poisson's and Laplace's equation along with the boundary conditions, and got a very important theorem and two identities. So, let us summarize this lecture. Derived Green's identities, 2 from Green's second identity, obtained Green's reciprocity theorem relating charges and potentials in a given volume, and third, applied reciprocity theorem to some problems, and also gave energy based derivation of reciprocity theorem. Thank you.